Next presentation is from Dr. Maren Brehme from ETH Zurich. Oh, there you Now, that's a lot of chocolate you're bringing up to the podium.
People who were with me last night, they know I eat a lot. So for 20 minutes I need that. Okay, thank you everyone. My name is Maren Brehme and I lead the Expo group at ETH Zurich. And we'll first introduce that a bit. So we are a team of around 15 people working within the GG group, which is led by Martin, who's also around. And I brought 4 students I will introduce later, and we have a lot of industry and academic partners around the world, which we collaborate with, because we are working on really applied topics. And to be open up front, I'm hiring at the moment, so I look for a postdoc currently working with me. So if you're interested, or if you know someone interested in the topics I present today, please reach out to me, and we can talk about that. You may wonder what EXPO means. It stands for Exploration and Operation of Geothermal Systems, so all of our research topics are about geothermal energy. And we work on local projects, on national projects, international collaborations. And we have basically 2 research questions we work on. You might saw them before in the circle. One of them is where to drill the next well, and one is how to operate these systems sustainably. So we try to find new sites, and I think only the combination of these 2 questions and the combination of all the answers to these questions is the solution, and to increase the worldwide use of geothermal energy. So where to drill the next well is an important question, because right now the worldwide statistics show that only 1 of 3 wells in geothermal projects is successful and producing and productive, and we can use it at the end for operation. And we should increase that, right? Because drilling is expensive. You will hear about this probably later. And the other problem is once the systems are running and we have successful wells, they run into problems very soon. So within 5 to 10 years, we always see a drastic productivity drop or injectivity drop. We have problems with corrosion. You see here one example from my colleague. She studied corrosion in a high enthalpy field, and they lost, for example, 80% of their casing within 1 year. And they had to close that well down, of course, right? Yeah, and then I hear a lot. Yesterday I heard a lot, and this morning again by Sebastian, we need data. We need to calibrate our models. Our models are wrong, or maybe only approximately right? So we are the team, reach out, please, we have the data, because we go to the field and measure the real data. We have data from geology, from fluids. We go to the geothermal sites, to the operator, and talk to them about their challenges. We get their data. So please reach out and let's collaborate to make your models right and to make use of our data, right? So in this presentation, I will focus on the exploration part, and the operation part I will introduce at the very end very shortly. If I would ask you to drill the next well on TU Delft campus, where would you put this well? If you look at this map. You don't have to know the campus, but you see it's highly kind of populated, right? There are a lot of buildings, so you don't have many options. TU Delft and our colleagues at TU Delft, they made a decision to where to put the well, but I think that was quite limited by the buildings. You had only one spot where to put them. If I would give you a few more options and give you the whole country of Netherlands to drill a well, where would you put that? Silence, as always. Yes, I don't know as well, right? We need data about the subsurface. But then if you even make it larger, zoom out, there's a lot of part of the Netherlands that belongs to the Netherlands, country of Netherlands, in the North Sea, right? So this part, which is blue here, and where I put the boat, because you can only reach it by boat, that also belongs to the country. So you could also put wells there, not only for oil and gas, but also for geothermal, right? And so my message is, out of this very beautiful blue planet, we miss out quite a bit, and that's the blue part. Right? We only focus on continents at the moment. We work onshore, but we can also work offshore. There's a lot of potential for geothermal energy projects offshore. And that is what we focus on with the new research laboratory that we build up with the support of energy simulation. We bought equipment. We went to field trips. But let me explain where this came from. So we did lake studies before, and we saw, for example, in this field in Indonesia, that there are two wells beneath the lake which are most productive in this field. They produce each 20 megawatt of electricity. And we wondered why they are so productive and the other wells in the field which are far from the lake are not so productive. So we went to this field and we studied that, and this is what we still do at other places in the world, two of them in Switzerland, in Lake Zurich and Lake Cardanio, which we did this year, and one again in Lake Ranau in South Sumatra, where we also did a field trip this year with the new equipment, and that's what I want to present to you today. So in Lake Zurich we had a bachelor thesis with Alexandra, you see here. She was very excited to be on the lake and to study with our new drone. So we bought a new drone, which is an underwater drone, you see on the top right. He's called Uwe, it's underwater exploration. And he can swim into lakes up to 150 meters deep. He can go down, he can take pictures, he can take videos. You can take samples from the sediments of the lake, he can take rock samples, he can take fluid samples, he can measure temperature, salinity, pH, he takes water samples for us. So all this blue area, which I just showed to you, is now accessible with this drone. And we did a first try here in Lake Zurich. You see what we call pock marks, or small holes, on this map, on the right side. And we wondered where they come from. So Alexandra's bachelor thesis was about these pock marks, and especially if they are active. So there are holes in the underground at the lake bottom, and we wondered if fluids come out here, right? Not that there is a very special potential of geothermal energy beneath Lake Zurich, but we wondered why are they there, because we see them also in volcanic lakes. So she went there, she drove the drone down to these holes. You see pictures here, and we found fractures in the underground. It was hard to detect fluid outflow or degassing, but we took sediment samples and sediment cores with another equipment. This is not what Uwe did, but we did also coring, and we could prove that these pock marks are inactive at the moment, and since the past 10,000 years, basically. We understood that they come from the glacier that was covering the lake in former times. So it's a glacial formation, basically, of these pock marks. And that there was degassing from these pock marks at that time when the glacier disappeared. That was a study more on hydrogeology, basically, and to test the drone just in front of our door, right? It's maybe a 3 kilometers walk from our university. We put the drone into the lake and could study and test it. So it was a first successful test of our new equipment. Then next we went to Lake Cardanio, which is a 3 hours drive from Zurich and the south of Switzerland. And we knew that this lake is special from the chemistry point of view. So there's stratification, and you see that on the picture to the right. You see a purple layer there. So there are bacteria active in this lake, and they form this layer of pink fluids, basically. And beneath that zone, there's no oxygen anymore. There's no fish, for example. There's no activity, but we knew that there are also springs underwater, and we were interested about these springs and why there's this chemical stratification. So we did a combination of bathymetry, and you see a map how we drove with a boat on the lake to cover the topography, basically, of the lake bottom. And then with the drone, you see on the videos, we were exploring the hot springs or cold springs we didn't know at that time, right? And you see that there are real holes in the underground. And if you look a bit careful, you see, for example now, that there's a blue fluid coming out of these springs. And there's some degassing, so we found active springs in this lake. This is a map of the bathymetry at the end, so we could map the topography of the lake. We could map the springs, what you see, that you see here. In this area, if you look a bit more careful, you see small circular structures, and these are the springs that we found. There's also one purple layer in the topography map now, and this is the purple layer at 12-meter depth. And in the video also right now, you see that the water is turning really purple, right? So we crossed these different zones of chemistry in this lake and understood about this evolution of the springs. We took samples from the water, which are now in the lab, so this is an ongoing master thesis. We took samples for biology, which are now analyzed right now. We took solid samples from the lake bottom and will understand the source of the fluids from the springs, and combined with the geology, we also want to understand why the springs only occur on this part of the lake, right? Not in the deep part, but in the shallower part. The springs are only in the orange area somewhere here. All right, then let's fly over to Indonesia. This is a very nice industry collaboration we set up. We signed an agreement. Once we arrived there, we joined the ITB Geothermal Conference in Bandung and met our industry partner, which is PLN. It's a state electricity company. And they are now exploring new geothermal fields. One of the fields is located in South Sumatra, like near to the lake, Ranau, which you see here. It's on top of the Sumatra Fault, basically. And there are also some data already available, but they didn't understand the system totally. So they found, for example, a very non-typical clay cap at the top of the volcano. And the question is not if there's potential, there's geothermal potential, but the question is where to drill, right? That was our first question, where to drill the first well. So we went to the field, we did structural geological mapping, we did fluid sampling from springs, but also from the lake again. You spent a lot of time on these very uncomfortable motorcycles, running around with you in the hills, taking fluid samples from the springs. We spent a lot of time on the boat, and you see again a map of the bathymetry path that we did. It's a huge lake, so we couldn't cover all of the lake, but we focused on the areas where the springs are. So in this case, we don't have underwater springs. So at the end we found underwater springs, but first of all, they knew about onshore springs, so we focused on that part for the bathymetry. In the video, you see that one capture of the springs that we found. So there's a lot of degassing activity here. On the right side, you see a picture that Uwe took, the drone again. We were flying with a drone underwater, where there's degassing. There are fractures that we found. We took rock samples from the underground. This is from roughly 60 meters deep, but we even went deeper with Uwe to 100 meters. On the left part, you see a very rough conceptual model that we have for now. So we found traces of faults and fractures in the underground. The bathymetry that we did is not ready yet, but I put another example, what it would probably look like from another lake that we found, where a huge fault is entering the lake and then leaving the lake again, and we can find the structures of the fault in the lake at the lake bottom, so we can map it, and nobody knew before where the fault is actually going once entering the lake. And then, as I said, we also took fluid samples from the hot springs. We have two different types, basically, and we saw this raising gas bubbles from the underground in the lake, but also in the hot springs. So this is what we are able to do with Uwe, our drone. And it's very exciting to do that, right? It's a lot of fun. It's quite exhausting, but now we have real data from the field, and I'm happy to share them. If you have models, if you're interested, then just reach out. Okay, and then in the second part, I would like to introduce a collaboration we did with Roman once during his sabbatical at ETH. We focused on a national study of Switzerland, on the geothermal potential of Switzerland, and used a techno-economic approach. And to also say it, all the detailed question goes to Roman, right? So we focused on different types of geothermal systems, right? A minute ago, we were focusing on Indonesia. There, of course, we have hydrothermal systems. We use open-hole systems. There's fluid available in the underground, but in Central Europe, we also think of open-loop EGS systems and also closed-loop systems recently, right? These are the three basic technologies we focused on. And Rebecca, she was a bachelor student working with us for 3 or 4 months. She focused on the whole country of Switzerland and thought of where's the highest potential for each of these systems. Where should we do in Switzerland build a hydrothermal geothermal power plant, maybe an EGS plant, or an open loop system? And we did a combination of data from the surface and the subsurface. So we looked at the building density. What does it tell you? It tells you where the heat or the electricity is needed, actually, right? You don't want to have a geothermal power plant where it's not needed. Then also you need roads and also transmission lines to first build the power plant, but also then to transmit and distribute the electricity or the heat, right? And then you already see there's a difference between heat and electricity. If you transport heat, you lose a lot. If you want to transport electricity, that should be easier if there are transmission lines available. If not, that adds costs to your project. And then, of course, the highest cost is always related to drilling. So she also looked into the geology and looked how deep do we have to drill for certain temperatures, and where is the basement? And the basement means hard rock, means high cost for drilling. And she put that together, and there are many steps in between, of course, and many more maps, and there's a lot of data she put together. But at the end, she came up with maps and total costs for certain degrees we gave her, right? So 60 degrees, for example, for shallow or middle deep heating systems, middle deep geothermal systems. So that were the costs, and you see the red parts are the high cost, the greener parts are the lower cost. So in northern of Switzerland, you don't have to drill that deep, first of all, and there's a lot of more infrastructure, there are a lot of more people living in that part of the country, so it's maybe more favorable to put a geothermal power plant there. It's a bit similar for the higher temperatures, but you see also a bit difference. The conclusion Roman draws from the last picture is don't drill in the mountains, right? If you have 4,000 meter high mountains, doesn't make sense. You don't want to build a power plant on top of these mountains, right? That does make sense. But you see that in the valleys, there's still high potential for building these power plants. And at the end, she came up using this very complicated formula, at least for me as geologist, looks very complicated. With this map, a rough estimation where it would be feasible to put certain geothermal systems in Switzerland. So there are hydrothermal systems for thermal use, for electricity use, the blue ones. EGS systems, she suggested to put it in the very north, and open hole systems even more to the north at the border to France and Germany. That is based, as I said, on surface data and subsurface data. It's not as detailed geological studies as Sebastian just presented. We can improve there a lot, but at least it's a rough estimation on the potential of geothermal energy in Switzerland. Okay, so what is our takeaway? What did we learn? Water bodies, the blue part of our planet, can cover unknown potentials, and we should study them. We do study them. We have this new laboratory that we use, the new drone. It's accessible with this new technology, and we have even positive parts in this. You might be kind of scared or a bit of suspicious about the working underwater, but it's actually a nice land surface that you're working with, because there's no vegetation, there are no people, there are no roads, there are no buildings. It's just open geology in front of you. You just have to dive down and have a look. And the combination of mapping and sampling is the way we go forward and we find successful. And for the second part, we understood and we saw that geothermal exploration on a national basis should be kind of structured, should be organized. There are a lot of things going on the national level anyway with the governmental offices in Switzerland. And we want to propose just one way and one suggestion how to go with that. We have to lower the costs of pre-exploration with using all the data. That's also why we have this open data politic. So if you're interested, we're happy to collaborate. And what we learned, Energy Simulation Chair, is collaboration is fun and success. So we enjoyed the sabbatical with Roman and ETH. It was nice to have you. One major conclusion from this study we do on exploration is that with our industry partners, and I just named the three that we worked on with in the past and that these statistics came up with, that we are able to increase the drilling success by roughly 15%. So you see a black line in these statistics. It shows the megawatt electricity output of wells and the well number. So it's basically the time and the output of wells. And you see that the successful wells, the red ones and the green ones, increased after the black line. And the black line marks the point where we as researchers came into that project and were able to help the industry partners and the operators to make a decision where to drill the next well. And so that drilling success increased by 15%. So you may wonder, we are the Expo group, and I only talked about exploration, but I We also work on the operational part, as I said, and I brought 4 students. Maybe you can raise your hands. It's Anna and Nicholas. Sarah, yeah, and Abel. So they all have a poster today in the next room, and please visit them to learn about clogging, about injection problems, about how to use oil feeds for geothermal energy extraction, and also how to avoid this clogging using CO2 in the underground for geothermal energy extraction. So please visit them to learn about this second part, which I couldn't talk about today. And then I want to thank our sponsors, Energy Simulation, for having us here, inviting us. Again, we are hiring, and if you're interested in more, just scan the QR codes. And then because it's a lot going on behind the scenes, I brought a small present for the 4 energy simulation people that did the most, I think. So Andrew and Hugh, thank you very much. I have this small Swiss taste of Switzerland for you. I give it to Andrew, that's fine.
Wonderful.
And Aneta and Ricardo, I have one for you too. I don't know if I put it here, okay? Yeah.
Okay, thank you. Excellent, thank you. Questions? Any questions from okay, Sebastian.
Thank you, Maren. Really nice presentation. On the project that you worked on with Roman, did you also look, like you mentioned EGS, which is always tricky with induced seismicity. Did you sort of also look at the seismicity risk and overlay this with sort of your analysis? Because then you can almost get with a traffic light where you have the right heat, not enough population, the right infrastructure, and not enough seismic risk.
Yes, we did. There's a very nice map provided by SED, by the Swiss Seismological Survey. Yes, we did overlay that and included that. I didn't show all the steps, but yes, we did.
Thanks.
Yeah.
Hi, Maren. Fantastic. Love the getting real data. That's outstanding. So there were a couple of things I was wondering about now in the lake, for instance. Love the drone. I thought I was having fun with 3D printing, but the drone thing is like, okay, you win. Almost having the sort of towed fiber optics. So you're listening to springs and you got the drone and everybody's having fun around, but you wonder about this sort of ambient noise interferometry stuff with a sort of a towed fiber buoyant in the lake and then just letting it sit and actually being able to listen and locate underwater locations. I wonder about your thoughts on that technology for field acquisition. Yeah, anyway, I'll just, lots of other questions, but it's just interesting.
Yeah, very good point. Thank you, Rick. Yes, well, this is a very promising technology, I think, that we should include, that we should use. I didn't mention geophysics here. For me, this is part of geophysics, and I'm very happy to include our data with geophysical data. We are not able to use all technologies, but we try to keep our team and the equipment very small that we bring to the field, because we fly far. We go to Indonesia with many big boxes, have to go through customs. That seems easy, but it's not. So we try to keep it small, but if there's a technology that we can include into the drone that we are developing now, so we bought this drone basically, but now we also have Niels, our technician, who's working on the drone and building new parts and reassembling. And so if you have ideas, I'm very happy to learn about that. If they are kind of small technologies that you can additionally bring and maybe place with the drone, leave it there for our field work, do other stuff, and take it after a week or so. I think it's very promising. Yeah, exactly. Yes, sure, great idea. Yeah.
Hey Maren, thanks for the very good presentation. This is a follow-up of this conversation as well. It's we had this kind of salt caverns for hydrogen storage, and there is also always a kind of a question whether we can send some sort of robots inside and then can do in situ monitoring. We had some sort of innovative proposal that was rejected successfully, but so the challenge there is actually to make it very small, that it would go through. And then I was actually wondering if your submarine drone type of thing, does it have gas chromatography inbuilt, or it's mainly just simply it would take you samples to the surface and you do the analysis? And where is the technology in the scale actually, how small they can be? Yeah, thanks.
Yeah. I think that we bought nearly the smallest drone that we could find, which is like this. We're flying with hand luggage with him, so he's really small. The equipment, he's on a cable for live data transmission. It's not like an airborne drone that really flies, but it's always on a cable. So all the cable and all the stuff is in the luggage. He himself is very small.
But does it have a kit that is smaller than him, or?
No.
I mean, he's that
Not
big.
yet.
Not yet.
But we're waiting, maybe in 9 months.
Yeah, exactly. Yeah, sure. Okay.
No, that's the smallest we could find that meets our needs, I would say. There are larger drones that can do much more. There are smaller drones that can do much less. That was the sweet point, I would say.
Thing we were working with a company in Munich. Actually, that company was very much expert on these sort of systems, and there was a permanent device launched in the cavern, and there was a mobile robot that would fly inside and then come back to the base, and then would do all the analysis, etc.
Yeah.
And they wanted to make it small, but yeah, that was anyhow.
I'm happy to learn more about that. I think I heard a bit about that project idea before, to lower it also down into wells. We cannot, maybe the first part of the well, but
Yeah, the wiring problem, for example, would be minimum. In that case, you have a base there, and then there would be flying objects and coming back to the base.
Yeah, if you go into water,
If
you
they are
always
not lost, by the way.
Yeah, we also get lost with Uwe. No.
Oh, okay.
Well, coming back to your question on the gas chromatography, if we measure in situ, this is our ultimate goal. At the moment, it's hard to make it pressure safe and tight, basically, underwater. There's no technology to do that in 100 meters below lake surface, right? But it would be the ultimate goal. At the moment, we only take samples and bring them to the surface. We are working with people developing these technologies and hope to implement that at one point, but at the moment we don't have.
Okay, so back many years ago when there was an SPATC at Disney, California, Saudi Aramco hosted a big session, and they talked about a dream technology in nano robots, basically really small nano robots going through a pore space and actually track the temperature, record the temperature as they go through the system and come back up. Is there some technology like that has been developed already? Or?
Well, I'm not very sure if you get the question right, but we are tracking the temperature as well. So we have the live tracking of temperature.
As the robot would go through the system?
Yeah, there's a live tracking of temperature. And also of salinity. We also have an underwater GPS system, so we can track where it's going actually. So we are not lost all the time. But if the GPS is working, then we know where we are, and we can go back to points of interest. Again, the Uwe was the sweet spot of what we needed, right? So you need a certain battery last time. We always have a battery also at the surface, but Uwe can go for like 2 or 3 hours on his own. Then you need to plug in another battery. So there are kind of technological limits at the moment that if you want to see where you are, that you have very strong lights in the front to see, because it's dark and 50 meters and 100 meter steps. So you cannot make it, I think for our needs, you cannot make it smaller at the moment. Then you would lose some abilities.
I really appreciate the work that you're doing in terms of the kind of better defining through your exploration where the sources are, and a lot of I guess negative sentiment against geothermal is that it doesn't work, it fails and whatnot, mainly because of not drilling at the right location. So besides that, what would really kickstart a big geothermal industry you could see?
Make it cheaper.
Which would be drilling and other aspects of it.
Make drilling cheaper and share more data. I think many countries also have a lot of data, or the companies have data, but they don't share. So people start from zero, basically. And then also when I go to the operators and talk to the companies, I tell them, come to us early, because we are interested in applied questions, and we have the time and maybe the funding and capacity to study certain things. I have one example from Lithuania, actually, where the company was quite late working together with us, but there was a kind of, at the end we discovered kind of vicious circle where certain processes influenced each other, and made the power plant at the end stop and bankrupt. But you could understand these processes if you have the data from the beginning, right? Before it's going into operation, or within the first years at least. And that's what my students partly work on, to understand these problems up front and not run into them and then try to solve them.
Great. Good point. Thank you. Once again, thank Maren for your good, interesting talk here.